This is a video lecture for visually impaired students. Chapter number 1, Metal Ligand Bonding in Transition Metal Complexes, from Pradeep's Inorganic Chemistry, Volume 3 by Dr. K. Bhasin. Valence bond theory. Valence bond theory was developed by Linus Pauling. According to valence bond theory, the bonding in metal complexes arises when a filled Ligand orbital containing a pair of electrons overlaps with a vacant hybrid orbital on metal ion to give a coordinate covalent bond. Thus, valence bond theory assumes the bonding between the metal ion and the ligands to be purely covalent. The hybrid orbital that a metal atom uses in accepting the pair of electrons from the ligands are those that point in the direction of the ligands. Valence bond theory successfully explains the structures and magnetic properties of coordination compounds. The salient features of the theory are recapitulated below. The central metal atom or ion in the coordination compounds offer a number of vacant orbitals which is equal to the coordination number of the metal ion for the formation of coordinate bonds with the ligands. The approximate atomic orbitals sp and d of the metal hybridize to give new set of orbitals of equivalent energy called the hybrid orbitals. The hybrid orbitals are directed towards the ligands depending upon the geometry of the coordination complex. The d orbitals involved in the hybridization may be either inner n-1 d orbital or outer n d orbitals. Thus, hybridization in case of octahedral complex may involve d2sp3 or sp3d2 depending upon whether inner or outer d orbitals are used for hybridization. The vacant hybrid orbital of metal ion overlap with the filled orbitals of the ligand and form a coordinate bond, that is L2M bond. Let us take some examples to highlight the feature of valence bond theory to complexes with coordination number 4 and 6. Complex with coordination number 4. Coordination compounds with coordination number 4 are well known. Complexes with coordination number 4 can be either tetrahedral or square planar depending upon whether the hybridization is sp3 or d2 dsp2 respectively. Some of the most commonly found examples are discussed below. Formation of NiCN42 negative ion. The oxidation state of nickel in the complex sign NiCN4 2- is +2. We can represent the electronic configuration of Ni2 positive ion by losing 2 electrons from the outermost 4s orbital. Electronic configuration of nickel is argon 3